Hey everyone, so we're looking at the last section for chapter 4 here, which is section 4.4, and this is where we're going to talk about the trigonometric form of a complex number. So basically, how can we rewrite a complex number in a trigonometric form? So of course, in section 4.1, we talked about how to add, subtract, multiply, and divide complex numbers, right? But what happens if you wanted to look at powers and roots of complex numbers? So in this case, it is actually better to write it in a trigonometric form, and then we can use the rules from trigonometric forms to help us work through those numbers. So they are talking about, think of the non-zero complex number a plus bi, and they're showing you that being plotted as a point right here in the graph here. So they're saying let theta be the angle that starts at the positive real axis and goes counterclockwise till it gets to that line segment, which will be connecting the origin to the point AB. So basically, this is our line segment going from AB to the origin right here, and then angle theta, basically, if you remember in terms of just trigonometric angles, this is starting at the initial side and going counterclockwise. You will go to that line segment, and that's going to be your angle theta over here, okay? And then basically they are saying that using this information of angle theta and this distance of the line segment going from the origin to the point AB is what we're calling distance r, and that r actually can be defined as using your absolute value formula that we saw in section 4.3, or if you think of this as forming a little right-angled triangle, then the definition of r can also come from the Pythagorean theorem. So r is defined as square root of the quantity a squared plus b squared. So using this r value and the theta that we just calculated by using this idea of the counterclockwise measurement that goes from the positive real axis to the line segment, you can actually define the a value as a equals r times cosine theta and b as r times cosine theta. So if we use this definition for a and b and put it into our complex number, so a will become r cosine theta plus b will become r sine theta, and then of course you have the I, so you multiply the b quantity with that I value, and this is how you end up getting the trigonometric form of our complex number. So basically we need the r value, which again is defined as square root of a squared plus b squared, and then theta is going to be the angle that is again, as you can see in the image. So using these two, we can convert our complex number into a trigonometric form. Okay, so let's go ahead and take a look at this definition here. They're saying the trigonometric form of the complex number z equals a plus bi is going to be, and basically, you know, what they're doing over here is you can see how both of these have an r in common. So we're actually bringing that r value outside as a common factor, and then you are left behind with cosine theta from the a term, and we are left behind with the sine theta from the b term, and of course that b will also have the imaginary number I on it. So that's basically how they are rewriting this form over here in trigonometric form. So you can have z equals r on the outside as our greatest common factor, and then cosine theta plus I sine theta. And if you wanted to distribute that r, you would end up getting r times cosine theta plus I, and then r times sine theta, and it would end up looking like this term over here. So you can even expand it the way you want to. So again, we're defining a as r times cosine theta, b as r times sine theta, r is defined as square root of a squared plus b squared, and here's how we define tangent. We define tangent theta as b over a. So basically we are saying that if you take the tangent of this angle theta, you should get the values b over a, or basically you can use b over a to come up with the tangent theta of this angle theta over here. So just as terminology, we refer to r as the modulus of z, because of course that's the modulus, or think about it as the absolute value from origin to that point AB. And then we refer to theta as the argument of z. Okay, so r is the modulus of z and theta is an argument of z. Now the trigonometric form of the complex number is also called the polar form, and you can technically have infinitely many choices for that angle theta, right? If you think about the coterminal angles. However, so they're just saying that the trigonometric form is not going to be a unique form since that angle can keep changing. But normally we define theta and restrict it to be between 0 and 2 pi. We're including 0 but not including 2 pi. And then depending on when we're solving these problems and if it's convenient, we can also think of theta as being a negative angle. Otherwise, normally we think of theta as going from 0 to 2 pi, including 0 but not including 2 pi. Now this will come in really handy, this remark over here. So when we restrict our theta between 0 to 2 pi, and if we know that our complex number z lies in the first quadrant, then to find theta, you can basically use theta equals arctangent of b over a, right? Because if we are defining tangent of theta as b over a, then to get theta by itself, you can basically use arctangent on both sides. So that's where they're getting this definition from. Theta equals arctangent of b over a. If our complex number z lies in the second or the third quadrant, then you want to use theta equals pi plus the arctangent of b over a, right? Because if you are going to be in quadrant 2 or quadrant 3, then of course pi is going to play a big part in that. If you're in quadrant 1, then of course we don't have to worry about pi because your angles are going to stay between 0 and pi halves. But when you go to quadrant 2 or quadrant 3, you're going from 0 to pi, or you're going from 0 all the way to 3 pi halves, right? And if our complex number z lies in quadrant 4, then you want to calculate your theta as 2 pi plus arctangent of b over a, and that's of course going to be our quadrant 4 angle over here, because that's when you have to consider the fact that you will be making almost a full circle to get there. Okay? All right, so let's see how we can actually do these examples. So we are given the complex number z equals negative 2 minus 2i square root of 3, and they want us to write this in the trigonometric form. So remember, to convert it from a complex number to a trigonometric form, we need the value r and we need the value of theta. So the first thing we are doing is calculating r, and remember again, r is defined as the square root of a square plus b square. So of course our a value here is negative 2 and the b value is negative 2 square root of 3. So that's why we have negative 2 squared over here and negative 2 square root of 3, the quantity squared over here under a square root, and this is just showing you the absolute value symbol over here. So simplify this. This will come out to be square root of 16, and square root of 16 of course is 4, so that's our r value. Now we need to figure out what our argument theta is going to be. So again, start out with tangent of theta equals b over a. So again, our b value is negative 2 square root of 3 over a value, which is negative 2. So your negative 2 cancel out, leaving you behind with square root of 3. Now, if you just look at this ordered pair, negative 2 and negative 2 square root of 3, you will see that our angle is actually going to fall in, our complex number is going to fall in quadrant 3. So if this is going to be in quadrant 3, then that means we have to use theta equals pi plus arctangent square root of 3. And think about where do you get or what will be the value of arctangent of square root of 3? Now, if you want, you can also use the unit circle to help you out. And what I actually do is I look at tangent of theta equals square root of 3, and I know tangent of theta equals square root of 3 happens right here at pi over 3, because when I divide square root of 3 over 2 by 1/2, I will end up getting the answer of square root of 3. So that's how I know we're looking at pi over 3. So when you do arctangent of square root of 3, of course arctangent of square root of 3 is going to give you the answer pi over 3. So add that pi over 3 with pi, simplify that, and you should get the answer of 4 pi over 3. So now that we have r, which was equal to 4 over here, and we have theta equals 4 pi over 3, and of course we know, and you can verify, 4 pi over 3 is going to be an angle in quadrant 3, which is what we want, since that's where our complex number is going to be. Then all you are doing in this formula here, replacing the r with the number 4, and then replacing the theta with 4 pi over 3, and that's how you go from your complex number, negative 2 minus 2i square root of 3, into its trigonometric form, which is this answer over here. Okay, so let's go ahead and take a look at our problem over here. They're asking us to write the complex number z equals 6 minus 6i in trigonometric form. So let's see what that will end up looking like. And you know what, just so that we can see what quadrant this will fall in, let's go ahead and do a little coordinate plane over here. And of course this will be our real axis, and this will be the imaginary axis. Okay, so this will of course give us the ordered pairs 6 and negative 6. So 6 and negative 6 will be positive 6 on this side, negative 6 here. This is just a rough sketch. It's not going to be, but you know, at least it gives us an idea of what quadrant we are looking at. So this is going to be where 6 minus 6i is going to be. So as you can see, this is a quadrant 4 number. So of course, remember, you calculate your theta going from the initial side or the positive real axis to that line segment. So this is going to be our theta, and then that distance of the line segment, or the absolute value of our complex number, is going to be our modulus r. So let's start by calculating our modulus first. Sorry, that should be modulus of z. So that's going to be taking the absolute value of our complex number, which will be defined as 6 squared plus negative 6 squared, which will of course give us square root of 36 plus 36, and that of course comes out to be a total of 72. And of course we need to simplify this. So if you think of square root of 72, 72 is going to be 36 times 2. So square root of 36 will come outside as 6, and square root of 2 will stay as it is. So this is going to be our r value. Okay, now that we have found the r value, now we want to go ahead and find our theta, because that's the other thing we need here. So let's look at argument theta, and remember the relationship for theta is tangent of theta equals b over a. So our b value is negative 6, a value is 6, which of course comes out to be negative 1. Now if we think about where do we get a tangent theta of negative 1, we can go back and look at our unit circle over here. So positive 1 of course will come out to be at pi over 4, but in this case, if you think in terms of clockwise, then -1 is actually going to be at this angle, which as a negative angle, this will be the same as negative pi over 4, right? If you go in the clockwise directions, if you go in this direction, our angle would be negative pi over 4. Okay, so let's see how we can find out what our theta value is going to be. So remember, since this is a quadrant 4 value, for quadrant 4, we do 2 pi plus our tangent of b over a. So that's what we're going to need to do here to find our theta value. Okay, so we will say since z equals 6 minus 6i lies in quadrant 4, there we go, lies in quadrant 4, we will have to use theta equals 2 pi plus arc tangent of b over a. So that will be 2 pi plus arc tangent, and of course our b over a came out to be -1, so that's going to be 2 pi plus negative pi over 4. So when you do 2 pi plus negative pi over 4, of course that will come out to be 2 pi minus pi over 4. Now we'll of course need to find our common denominator here if we're going to subtract these two numbers, and you will end up getting 8 pi over 4 minus pi over 4, and of course that will come out to be 7 pi over 4 as our theta value. And of course that's no surprise, right? Because in the counterclockwise direction, this would of course be our theta angle. Let's call this theta prime. You will of course come out to be at 7 pi over 4, so that's the same number that we got over here. So now that we have our r and the theta values, we can rewrite our trigonometric form for the complex number. Okay, so this will come out to be, remember, z equals r times cosine theta plus I times sine theta. So r was again 6 square root of 2. There we go. And then cosine of theta will be 7 pi over 4 plus I sine of 7 pi over 4. And this is going to be our trigonometric form for the complex number 6 minus 6i. Okay? Alrighty, so let's go ahead and see what the second one is talking about here. It's very similar. They're asking us to write the complex number 6 plus 2i in the trigonometric form. So again, start with your modulus. And that's going to be square root of 6 squared plus 2 squared. 6 squared, of course, is 36. 2 squared is 4, so 36 plus 4 gives you 40. Simplify that, you get square root 2 times square root of 10. Then tangent of theta equals b over a is of course going to be 2 over 6 or 1/3. Now if you look at the unit circle, you are actually not going to get the answer of 1/3 for any of these theta tangent measurements on the thetas. So that means we actually have to use our calculator to find the arc tangent of 1/3. You can do it as a radian or as a degree, but in this case we'll leave it as a degree measurement. So we have our theta, we have our r, so now we can put it in this form and you end up getting the trigonometric form of 2 times square root of 10 multiplied by cosine of 18.4 degrees plus I sine 18.4 degrees. Okay, so let's see what do we get for our example over here. Z equals 3 plus 4i. Alrighty, so again, let's go ahead and do a little, not view, a little graph over here so we can see what quadrant this falls into. Okay. Come on, there we go. Alright, so we will have this as the real axis, and this guy of course will be our imaginary axis. Okay, so this will be the ordered pair positive 3 and positive 4, so positive 3, positive 4 somewhere over here, or the number 3 plus 4i. So our complex number is in quadrant 1. So of course when you're talking about theta, we are just looking at this angle here, and this of course will be our modulus r. So let's start by again finding that modulus of z. So this will end up giving us r equals the absolute value of 3 plus 4i, which is going to be square root of 3 squared. Come on, buddy. Plus 4 squared, which will of course end up giving us 3 squared is 9, 4 squared is 16, 16 plus 9 gives us 25, which will of course give us 5 as our modulus. Okay, now that we have the r value, we of course need to find our argument theta. So again, we use tangent of theta equals b over a. So that will be 4 over 3. And 4 over 3, again, is not a value you are actually going to see in your unit circle. So since this, again, does not work for our unit circle, we will go ahead and use arctangent of 4 over 3 and then use our calculator to simplify that. Okay, so again, since our z value lies in quadrant 1, we will just use theta as being arctangent of b over a. So of course that will be, in our case, arctangent of 4 over 3. So if we put this in our calculator, this comes out to be approximately 0.927295,218, and this is in radians, and if you want to convert this into degrees, it comes out to be approximately 53.1 degrees, and we're just rounding this off to 1 decimal place like our example. Alrighty, so we've got the r value, we've got the theta, so we're ready to convert this into the trigonometric form. Oh, looks like I missed something in there. There we go. So the trigonometric form of z, again your formula is r times cosine theta plus I sine theta. So r was 5, and this will be cosine of 53.1 degrees plus I sine of 53.1 degrees. Okay, and there you go. This is our trigonometric form for z3 plus 4i. So the two examples you just saw, one of them we were able to use the unit circle to find the exact angle where our trigonometric form would fall for the complex number. And in this example, of course, you saw we have to use a decimal approximation since we can't really calculate where tangent of theta will equal 4 over 3. Okay? Alrighty. Now, let's see how we can write a complex number in standard form. So here you will see we are given our number in the trigonometric form. So you have z equals 4 times cosine of 120 degrees plus I sine of 120 degrees. And they're asking us to write it in the standard form of a plus bi. So first go ahead and calculate what the cosine and sine values will be. So cosine of 120 degrees and sine of 120 degrees, you can actually use the unit circle here. So again, that gives you the negative 1/2 for cosine, square root of 3 over 2 for sine. So this is where we are getting these answers from. And then when you go ahead and replace this with negative 1/2 and this guy here with square root of 3 over 2, so that's where we are getting negative 1/2 plus I times square root of 3 over 2. And then what happens is once you rewrite this, then distribute that 4 inside the parentheses. So this 2 on the denominator will go ahead and cancel out that 4, and that's how you end up getting negative 2 plus, and again, I would actually write this as negative 2 plus 2I square root of 3. Put that I in the middle, okay? So that's how you end up converting it from a trigonometric form into a standard form for the complex numbers. So let's see what we can do with our example over here. So we are given z equals 2 times cosine of 150 degrees plus sine of 150 degrees. So let's go ahead and see what cosine of 150 degrees and sine of 150 degrees are going to be. So let's go back to our unit circle, and we're looking for 150 degrees, which is right here. So cosine is negative square root of 3 over 2. Sine is 1/2. So cosine is negative square root of 3 over 2. Sine is positive 1/2. So in our function over here, where you have cosine of 150 degrees, we'll replace that, and the sine of 150 degrees will also get replaced by these values we just saw from the unit circle. So cosine of 150 degrees is negative square root of 3 over 2 plus I. We'll leave that I as it is over there. And then sine of 150 degrees, of course, is 1/2. Now, we will need to distribute this 2 inside the parentheses. So you will have 2 times negative square root of 3 over 2 plus 2 times I times 1/2, right? That 2 on the denominator will cancel out this 2. Same thing here, 2 on the denominator cancels out this 2. And we end up getting, let's see, on the first half, just negative square root of 3 is left behind, plus I times 1 will just end up giving us I. So this is going to be our z value in the standard form, negative square root of 3 plus I. That's going to be your complex number. Okay? Alrighty guys, just another type of example where instead of degrees we are given the theta in radians. So here you are given z equals square root of 8 times cosine of negative pi over 3 plus I sine negative pi over 3. And again, we're putting this in the standard form of a plus bi. So cosine of negative pi over 3 and sine of negative pi over 3. Again, you can go to your unit circle. So positive pi over 3 is here. So this guy here is actually your negative pi over 3. So cosine is 1/2. Sine is negative square root of 3 over 2. So you can see cosine is 1/2. Sine is negative square root of 3 over 2. So go ahead and replace these values here with positive 1/2 and negative square root of 3 over 2. So that's where these numbers are coming from. And then again, distribute that 2 square root of 2 inside the parentheses. The 2's will cancel out, leaving you behind with this answer. And again, I would write this guy as square root of 2 minus I square root of 6. You always want to write that I before the radical, okay? All right, so let's see what we can do with our example here. Z equals 8 times cosine of 2 pi over 3 plus I sine 2 pi over 3. So that's the first thing we want to do, is figure out what cosine of 2 pi over 3 and sine of 2 pi over 3 is going to be. So let's go to our unit circle here. 2 pi over 3 is the same as the 120-degree angle. So that's going to be cosine is negative 1/2. Sine is square root of 3 over 2. So negative 1/2 for the cosine and square root of 3 over 2 for the sine. So again, in our complex number, we will rewrite cosine and sine of 2 pi over 3 using this information, and that will give us cosine of 2 pi over 3 will be negative 1/2 plus I times sine of 2 pi over 3 will be square root of 3 over 2. Just like you did in the previous example, distribute this 8 inside the parentheses, and we end up getting 8 times negative 1/2 plus 8 times I times square root of 3 over 2. So since we have a 2 on the denominator, again 2 goes into 8 4 times, 2 goes into 8 4 times, and we will end up getting 4 times negative 1 is negative 4, plus 4 times I times square root of 3 will be 4I square root of 3. And this is again converting it from the trigonometric form into our standard form. Okay, so hopefully these two examples helped you out to see how that transformation happens. Okay, now let's talk about what happens if we wanted to multiply or divide two complex numbers in their trigonometric form. So they are saying trigonometric form adapts nicely to multiplication and division of complex numbers. So let's see, these are our two complex numbers. So Z1 is R1 times cosine theta 1 plus I sine theta 1, and Z2 of course will be R2 cosine theta 2 plus I sine theta 2. So when you are multiplying, what happens is you end up multiplying the moduli, which is the R1 and the R2. So multiply the moduli together, and then you are basically going to multiply the parentheses parts together. So when you multiply the parentheses part, just do FOIL like you saw in section 4.1. But then what we are doing is we are separating the real part from the imaginary part, and then on each one of these real and imaginary parts, we're using the sum and difference formulas that we had talked about in, if I'm not mistaken, I think it was chapter 2, could have been chapter 3, I'm a little confused, but it was one of those two chapters where we talked about the sum and difference formula. I think I want to say chapter 2, but just go back and look through your handouts. And then when you clean this up, it actually simplifies into a nice simple formula over here by using that sum and difference formula. So the multiplication of two complex numbers basically comes out to be where you multiply the two moduli, so R1 times R2, and then you're still keeping that same format of cosine in the front plus I sine in the back, but for multiplication we go ahead and add our two angles. So that's theta 1 plus theta 2 coming from the two different complex numbers, and then same thing for I sine, theta 1 plus theta 2, you again end up adding. Now you can verify this same rule for the division, and exercise 73 in your textbook asks you to verify that the division will also work in the same way. But so you can see your multiplication rule over here, which we verified right over here. And then here's your division rule. So Z1 divided by Z2, again, this is where you divide your moduli. So R1 divided by R2, and then in the angles, we actually end up subtracting them. So you are doing cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Now, since we are dividing by the complex number Z2, you want to make sure Z2 is not going to equal 0, because we still have to think about division by 0 being undefined. Okay, so basically what's happening in the multiplication of the two complex numbers, you multiply the moduli and you add the arguments. Remember, again, arguments are the thetas. And then when you are dividing, you divide the moduli and you subtract your arguments. Okay, so let's go ahead and put this in action. So let's look at example 5 over here. We are given Z1 as 2 times cosine of 120 degrees plus I sine 120 degrees. Z2 is defined as 8 times cosine of 330 degrees plus I sine 330 degrees, right? So this is multiplication. So we'll multiply 2 times 8, which will end up giving us 16. And then we'll add cosine of 120 plus 330 degrees, which will of course end up giving us cosine of 450, same thing. Sine, you add 120 plus 330 degrees, which will end up giving you sine of 450 degrees. Now, if you just take that 450 degrees and subtract 360 from it, right? So going a full circle, you end up getting 90 degrees. So that's how it went from being cosine of 450 to cosine of 90. And same thing, sine of 450 to sine of 90 degrees, which of course is this point right over here, and that will have the coordinates 0, 1. So cosine of 90 is 0, sine of 90 is 1. 0 plus 1 times I just ends up becoming I, and then 16 times I gives you 16I. Okay, so that's how you come up with the product for Z1 multiplied with Z2. Now let's go ahead and take a look at our problem over here. So we are given Z1 as 3 times cosine of 60 plus I sine 60. And then Z2 is given as 4 times cosine 30 plus I sine 30. So let's see what this guy comes out to be. Alrighty, so we are multiplying these. So Z1 times Z2 will be 3 times cosine of 60 degrees plus I sine 60 degrees multiplied with 4 times cosine of 30 degrees plus I sine 30 degrees, right? Okay, so by our, I guess you can call it a product rule, you will end up multiplying 3 times 4 in the front, and then we'll end up doing cosine, and remember this is where you add your angle, so that's going to be 60 degrees plus 30 degrees for the cosine, plus I times sine, same thing, 60 degrees plus 30 degrees. 3 times 4 will of course give us 12, and then cosine of 60 plus 30 will add up to 90 degrees, plus I times sine will also be 90 degrees. And just to show you, 90 degrees of course is again right here at the pi halves, and that will have the coordinates of 0 and 1 for your cosine and sine values respectively. So cosine of 90 and cosine of 90, so again cosine of 90 degrees is 0, sine of 90 degrees is 1, so this will become 0 plus I times 1, which will of course just become I, and you end up getting 12I as your product for Z1 times Z2. Okay, and this only happened because our angle was at 90 degrees. If our angle was anything else, then you may not end up with just 12I. You would have some more terms in there. But this again just kind of gives you an idea of how the product rule works when you're trying to multiply two complex numbers in their trigonometric form. Okay, so our now here we're just talking about how you can also check your answer. So you can actually take these complex numbers that you have here in trigonometric form, and you can convert them into standard form, and then just use the method we saw in section 4.1, where you just go ahead and FOIL these two numbers, go ahead and clean it up, and you end up getting 16i as your answer, because you will see negative 4 square root of 3 will cancel out with positive 4 square root of 3, and then you're just left with 4i plus 12i, which adds up to 16i. So just another way if you want to check your solution. Alrighty guys, let's take a look at how does division work with complex numbers in their trigonometric form. So we are dividing z1 by z2. So we are given z1 as 24 cosine of 5 pi over 3 plus I sine 5 pi over 3. And z2 is 8 times cosine of 5 pi over 12 plus I sine 5 pi over 12, right? So z1 on the top, z2 on the bottom. 24 divided by 8 gives us 3. And then remember, for division, this is where we end up subtracting our angle. So you are doing 5 pi over 3 from the top minus 5 pi over 12 on the bottom, and we'll do the same for sine and cosine. Now we are given 5 pi over 3 minus 5 pi over 12. So of course we need to find common denominator. So this guy will be multiplied by 4, and you will end up getting 20 pi over 12 minus 5 pi over 12, which will of course end up giving us 20 minus 5 would be 15 pi over 12, and then both 15 and 12 have a 3 in common. So 15 goes into 3 5 times, 12 goes into 3 4 times. So that is where you are getting this 5 over 4, 5 pi over 4 and 5 pi over 4 for our sine and cosine functions. And then for 5 pi over 4, you can again go back to the unit circle. Here's our 5 pi over 4, which gives us sine as negative square root of 2 over 2, and sine also will be negative square root of 2 over 2. So if you rewrite this as 3 times negative square root of 2 over 2 plus, well, it should be plus and minus, so that'll just become minus I times square root of 2 over 2. So when you distribute this 3, that's when you end up getting this answer of negative 3 square root of 2 over 2 minus 3 square root of 2 over 2i. Okay? Alrighty folks, so let's take a look at our example over here. We are given z1 as cosine of 2 pi over 9 plus I sine 2 pi over 9, and z2 is given to us as cosine of pi over 18 and I sine pi over 18. Now you will notice for both of these complex numbers, we don't have an R value in front, like we had a 24 here and an 8 over here, right? So there are no R values in this example. So let's go ahead and take a look at this guy here. So to find the quotient, so z1 divided by z2, we will have cosine of 2 pi over 9 plus I sine of 2 pi over 9 divided by cosine of pi over 18 plus I sine of pi over 18. So like I said, no R values in the front, so we don't have to worry about dividing those R values. So you can go directly into cosine of 2 pi over 9, it's always the top minus the bottom, minus pi over 18, and then this will be I times sine of 2 pi over 9 minus pi over 18. So let's see what happens when we simplify that parentheses part. So 2 pi over 9 minus pi over 18. So again, find a common denominator. Between 9 and 18, 18 will be the common denominator. So multiply this guy by 2, which will end up giving us 4 pi over 18 minus pi over 18, and then 4 pi minus pi will give us 3 pi over 18, and of course you will see 3 goes into itself once, 3 goes into 18 6 times, so this will end up becoming pi over 6. Okay, so we can rewrite these guys as cosine, come on, there we go, cosine of pi over 6 plus I sine of pi over 6. Okay, so of course we can use our unit circle to find the value for cosine of pi over 6 and sine of pi over 6. So let's see what those guys come out to be. There we go. Alright, pi over 6 is right over here, the 30-degree angle, so that's going to be square root of 3 over 2 for cosine and 1/2 for sine. So square root of 3 over 2 and 1/2. Alrighty, so when you put this back in for these sine and cosine functions over here, we should end up getting cosine of pi over 6 is square root of 3 over 2 plus I times sine of pi over 6, which will be 1/2, so we can just write this as square root of 3 over 2 plus 1/2 I, and this will be our result for our quotient of z1 divided by z2, and that's the answer you come up with. Okay, so now you've seen an example for how the quotient or division of complex numbers work in trigonometric form and multiplication also. Alright, very good. Okay, so in the last section, we talked about how we can add, subtract, and find the complex conjugates of complex numbers geometrically in the complex plane, right? We use those vectors to help us out. So in that same way, we want to see how we can multiply complex numbers geometrically in the complex plane. So other than addition and subtraction and finding the complex conjugates, let's look at how to multiply geometrically the complex numbers in their complex plane, okay? So we're basically trying to find the product of z1 and z2 in the complex plane. So z1 is given to us as 2 times cosine pi over 6 plus I sine pi over 6. z2 is given to us as 2 times cosine of pi over 3 plus I sine pi over 3. So the first thing we're going to do is write each of these complex numbers as vectors. So let's use vector u for z1. So 2 times on the outside for this r value of 2. And then again using our vector notation, we've got cosine of pi over 6 for the first coordinate, sine of pi over 6 for the second one. And then again, you know, cosine of pi over 6 and sine of pi over 6 is square root of 3 over 2 and positive 1/2. So basically what you have is square root of 3 over 2 from here, 1/2 from here, and then when you distribute that half, it ends up canceling out that denominator, leaving you behind with just the square root of 3 comma 1. When we do vector for z2, we end up getting 2 times again on the outside for that r value, and then cosine of pi over 3 as the first coordinate, sine of pi over 3 as the second coordinate. So pi over 3, which is 60-degree angle, gives us 1/2 and square root of 3 over 2. So 1/2 for the cosine and square root of 3 over 2 for the sine. And again, when we multiply by that 2 on the outside, this 2 on the denominator cancels out, leaving us behind with just 1 comma, square root of 3. Okay, so this is what these two vectors come out to be. Now if you find the magnitude for each of the vectors, so that's basically going to be square root of 3 squared plus 1 squared inside the square root symbol. Clean that up and you get the answer of 4. Finding the magnitude of vector v, again same thing, it comes out to be magnitude of 2. Now if I take the product of both of these vectors, if I take the product, that means I am taking the product of the magnitude of u and multiplying it with the magnitude of vector v. So that's 2 times 2, which comes out to be 4. Okay, if we take, and you know, again, remember, why are we multiplying this? Because remember, we multiply z1 with z2, so that's why we also need to multiply the vectors that are representing z1 and z2, so that's why you're multiplying these. And then remember, in our product rule for multiplication, we go ahead and add up the two angles, theta 1 plus theta 2, in our multiplication. So that's why we are going to be adding the two angles over here. So that was pi over 6 plus pi over 3. Clean that up and it comes out to be pi halves. So what this is telling us, that these are the two original vectors for our complex numbers z1 and z2. And this is telling us that when we multiply, the direction of our product vector is going to be in the direction of pi halves, which is of course 90 degrees. So that's why it's going on this vertical imaginary axis on the positive side. And since it has a magnitude of 4, which is what we got here by multiplying 2 times 2, that's why you are going up to a distance of 4. And that's where you're getting this vector 0, 4. So the vector 0, 4 is basically telling us that our real number part is 0 and the imaginary part is 4i. So you are going to get a product for z1 times z2 as 4i. Now if you just use the product rule to multiply these, you can check your answer that way and make sure you still get 4i as your product by using what we did in example 5. Okay, so that's kind of how the geometric calculation will work out to be when you are trying to multiply two vectors. So let's go ahead and take a look at this example over here. We are given z1 as 2 times cosine of pi over 4 plus I sine pi over 4. And z2 is given to us as 4 times cosine of 3 pi over 4 plus I sine 3 pi over 4. So let's see how this guy will work out to be. So let's go ahead and actually see graphically what these guys come out to be. So this will be our real axis. And of course this will be the imaginary axis. Okay. So let's start with rewriting z1 as vector u. So that will end up giving us u as, again, that 2 on the outside, and this will be cosine of pi over 4, and this will be sine of pi over 4. Okay, so again 2 times cosine of pi over 4, again if you need your unit circle, will be square root of 2 over 2. Sine of pi over 4, which is the 45-degree angle, will also be square root of 2 over 2. So this guy will give us square root of 2 over 2, comma, square root of 2 over 2. And then of course we need to distribute this 2 inside these brackets, so you will end up getting, oh, hold on a second. So that will be 2 times square root of 2 over 2, comma, 2 times square root of 2 over 2. This 2 on the top cancels out with the 2 on the bottom, and we are left behind with square root of 2, comma, square root of 2. So square root of 2 is like approximately 1.4 something, right? So if we were trying to graph these, let's see where they would fall on our coordinate plane here. And of course, this is your imaginary coordinate plane. So square root of 2 about 1.4 and 1.4, so it's probably going to fall somewhere over here. Okay, so that will be, come on, there we go. This is our vector u. Now let's see what happens with vector v. So that's going to be for the z2. We are going to rewrite that as vector v. So vector v is going to come out to be 4 times cosine of 3 pi over 4 and sine of 3 pi over 4. So 4 times, and again cosine of 3 pi over 4 and sine of 3 pi over 4, so that's the 135-degree angle right here. 3 pi over 4, that will be negative square root of 2 over 2 and positive square root of 2 over 2 respectively for our sine and cosine. So negative square root of 2 over 2, positive square root of 2 over 2 again. Distribute that 4 inside these brackets, and we end up with 4 times negative square root of 2 over 2 and 4 times positive square root of 2 over 2. 2 will go into 4 2 times. Same thing over here. So when we clean this up, you should get negative, sorry about that, that will be negative 2 square root of 2, and this will be positive 2 square root of 2. So you are looking at approximately what will that be? So 2 times square root of 2 comes out to be approximately 2.8. So just double of the 1.4, right? So that will be negative 2.8 and positive 2.8. So negative 2.8, positive 2.8. This will be a vector somewhere over here. And I think I have it placed a little incorrectly, so that should be, so this guy here is going to be our vector v, okay? Now we want to see where that product of this two vectors is going to end up with. So let's look at the magnitude for each of these vectors u and v. So let's talk about magnitude of vector u, and that's of course going to be square root of square root of 2 squared and square root of 2 squared. So square root of 2 squared, not what I wanted to do. Okay, square root of 2 squared. So in this case, of course, the square will cancel out each of these individual square roots, giving us basically 2 plus 2 on the inside, which will be square root of 4, which gives us an answer of 2. And let's do the same thing, find the magnitude of vector v. So that will be square root of negative 2 square root of 2 squared plus positive 2 square root of 2 squared. So in this case, what's going to happen is this 2 will of course distribute with both the negative 2 here and square root of 2. Same thing with the square will distribute. So what you will end up getting on the first part, negative 2 times negative 2 will become positive 4. Square root of 2 squared will just become the number 2. And if you want to kind of see the breakdown, you are doing negative 2 squared and square root of 2 squared. This is coming from here. So negative 2 squared will become 4. The square root and square will cancel out, and you will end up getting 4 times 2. And that's the same thing that's going to happen here, except you don't have that negative on your 2 on the outside. Okay, so again, this guy will become plus 4 times 2. So we are looking at 4 times 2, which will of course be 8 plus 8. 8 plus 8 will give us 16, and square root of 16 will end up giving us 4. Okay, so we've got the magnitude for each of the vectors. Now let's talk about the magnitude of the product vector. So magnitude of the product vector is where we multiply each one of these magnitudes with each other. So that's going to be 2 times 4. Come on. Which will of course end up giving us positive 8. So now we know what the magnitude of the product vector has to be, but we still don't know what the direction has to be. So this is where we take the sum of the direction angles. So this is where our two angles were pi over 4 and 3 pi over 4. And here, of course, you can see we have a common denominator, so we can just add the numbers on the top, which will be pi plus 3 pi. Of course, that comes out to be 4 pi over 4. Since we have 4 and 4 both on the numerator and denominator, this ends up giving us the angle of pi. This basically tells us that our product vector is going to lie on the negative real axis, okay? Because that's where pi is going to be. So the product vector lies on the negative real axis, and it will be represented by represented by the vector as negative 8, 0, right? Oh, not a parentheses, because this is a vector. So we know our angle is going to lie on the negative real axis, which is this one right here, and we have 4, 5, 6, 7, 8. So our product vector is going to be lying on this side, and we know it's got a magnitude of 8, so since it's on this axis, it's got to be negative 8, and that means our imaginary coordinate has to be 0. So this is going to be a vector of negative 8, 0, and of course if it's negative 8, 0, then our product is going to be so z1 times z2 is going to give us a product of just negative 8, because that's on the real axis, right? It's not on the imaginary axis. So that means you're just looking at negative 8 as your product when we multiply these two complex numbers in the trigonometric form. Okay, so this was just to show you how the geometric form of the product rule works out for complex numbers in trigonometric form, okay? So I believe this is the last example we are looking at here in section 4.4. So again, go through these examples, look through the video, look through the handout, and let me know again, guys, if you have any questions. We'll go over more examples in class. So just be careful, be safe, and I will see you in class next time. All right, take care, guys. Bye-bye.